The clang of metal on metal, the flash of a spear tip meeting a breastplate, the instant a warrior knows whether he will live or die. What do you think about the power of protection? Let me know in the comments. This film follows a single line of evolution, each armor emerging only because its predecessor could no longer withstand the weapons of its time. 8 distinct armors will be traced, each one the answer to a battlefield problem that rendered the previous protection obsolete. The story moves forward without pause, each breakthrough forced by the relentless pressure of new offensive tools. In the earliest days of organized conflict, wooden shields shattered under the force of stone-tipped spears, and hunters needed a mobile barrier that could absorb blunt blows. The solution was hardened leather, thick hides boiled, cured with resin, and layered to create a flexible shell. Archaeological sites such as Catalhoyuk reveal where patterns consistent with repeated impact, and experimental reconstructions demonstrate that boiled hide can stop a heavy club strike while remaining light enough for rapid movement. The armor's weakness lay in its vulnerability to fire and to the emerging copper points that could pierce softened hide, prompting the search for a metal that could spread the force of a blow without breaking. Copper, being the first widely available metal, was fashioned the next generation of protection. Overlapping copper scales sewn onto a leather backing. The scales acted as a mosaic, each piece deflecting a portion of the kinetic energy and preventing a single point of failure. Graves in the Levant contain intact scale sets, and metallurgical analysis confirms a uniform thickness that distributes stress across the surface. Yet copper's inherent softness meant that as bronze alloying techniques improved, bronze weapons began to cut through the scale joints, exposing a critical gap in defense. The rise of bronze with higher hardness forced armor makers to seek a single-piece solution that could better resist cutting edges. Bronze breastplates arrived as a hammered, curved cuirass that covered the torso in one solid shell. The curvature forced blows to glance off, and the single piece eliminated the gaps that plagued scale armor. Mycenaean tombs have yielded complete bronze cuirasses, and contemporary Hittite records describe warriors whose bodies were clad in iron-like bronze, indicating a perception of superior protection. However, the bronze plate was heavy, limited limb coverage, and its tensile strength lagged behind the newer iron weapons that began to dominate battlefields. As iron smelting spread, swords forged from iron could split bronze plates with relative ease, exposing the need for a harder, more resilient material that could also be fashioned into a full-body system. Iron laminar armor answered that call. Stacked iron lamellae riveted to a leather foundation created a flexible yet rigid barrier that could absorb and distribute the force of iron swords. Fragments of Roman larica segmentata illustrate the precise rivet patterns that allowed movement while maintaining protection, and battlefield injury reports from the period show a marked reduction in torso trauma compared to earlier bronze armor. The laminar system, however, suffered from corrosion in damp climates and still left the limbs exposed, a vulnerability that would be exploited by the increasingly powerful crossbows and the first gunpowder projectiles. The emergence of high-carbon steel, capable of holding a sharper edge and resisting penetration, set the stage for a new era of full-body protection. If this is blowing your mind, hit that subscribe button and stay with me as we move to the next breakthrough. The next step in the chain will be the mesh of interlinked steel rings that would dominate battlefields for centuries, but that story belongs to the following segment. If you found this journey through early armor as compelling as I did, smash that like button if this hit different. The iron lamellae that had once turned the tide now left the shoulders, elbows and knees exposed, a gap that crossbow bolts and the first powder-charged projectiles could exploit with lethal precision. The solution arrived as a flexible lattice of steel rings, each link forged to a uniform diameter and interlocked in a continuous mesh that could be draped over the torso, limbs, and even the neck. Archaeological excavations of Viking burial mounds have yielded complete hauberks, their rings still tightly bound, while Byzantine military manuals of the 6th century describe the mesh as a shield that moves with the body. Experimental firing of replica longbows against authentic mail demonstrates that the interlinked rings disperse the energy of a cutting blade, preventing a single point of failure and allowing the wearer to retain full mobility on uneven ground. The mesh's greatest strength lay in its ability to absorb slashing blows while flexing around the wearer, a quality that made it the dominant protection across Europe and the Near East for more than 6 centuries. Yet the very flexibility that granted freedom also meant that a narrow, high-velocity projectile could force its way between the rings, and the cumulative blunt force of a heavy warhammer could still bruise the wearer through the metal. As crossbow technology refined and early firearms began to appear on the battlefield, the mesh's resistance to penetration waned, prompting armorers to seek a solution that could present a solid barrier without sacrificing the ability to fight on foot. The answer emerged as a series of articulated steel plates, each carefully shaped to follow the contours of the human form and connected by leather straps, hinges and sliding rivets that allowed the wearer to stride, crouch and raise a sword with a fluidity previously reserved for lighter protection. Surviving suits from the 15th century, displayed in major museum collections, reveal a comprehensive coverage that includes a breastplate, backplate, gauntlets, greaves, and a visor that can be lifted with a single lever. Contemporary chronicles of the 100 Years' War recount knights whose bodies were as hard as iron, a testament to the psychological impact of a fully encased warrior. Ballistic testing of reconstructed plates against period musket balls shows that the angled surfaces cause projectiles to glance off, while the overlapping joints prevent a single strike from breaching the armor's envelope. The plate's superiority rested on its ability to present a continuous, hard surface that could deflect both the kinetic energy of a lance thrust and the impact of a falling arrow, effectively neutralizing the threats that had rendered mail vulnerable. However, the extensive steel coverage added considerable weight, demanding a robust support system of padded gambesons and limiting endurance during prolonged campaigns. Moreover, the increasing power of muzzle-loaded firearms meant that a direct hit at close range could dent or even puncture the steel, a vulnerability that spurred armorers to explore layered constructions that could absorb and disperse the energy of a high-velocity round without becoming prohibitively thick. The next evolutionary leap combined the hardness of steel with the energy-absorbing qualities of softer, resilient materials, creating a laminate that alternated thin steel sheets with layers of treated leather, silk, and, later, early polymeric fabrics. Surviving cuirasses of the early 17th century, particularly those used by the Swedish infantry during the 30 Years' War, display a sandwich of steel on the exterior, a middle core of tightly woven silk, and an inner backing of hardened leather, all bound together with animal glue and iron rivets. Contemporary testing of these composites against period musket fire shows a marked reduction in penetration depth compared to solid steel plates of equivalent thickness, as the silk layer spreads the shock wave across a broader area, while the leather core cushions the impact. The laminate's advantage lay in its ability to stop a musket ball without requiring the massive weight of a solid steel plate, allowing soldiers to maintain maneuverability on the battlefield while still enjoying a level of protection that far exceeded that of earlier mail or plate alone. Yet the manufacturing process was labor-intensive, demanding skilled artisans to align each layer precisely, and the composite remained vulnerable to repeated cannon fire and the emerging rifled firearms that delivered higher velocities and more concentrated impact. As industrial production of firearms accelerated and battlefield artillery grew in both range and power, armorers recognized that even the most sophisticated laminates could not reliably stop the new generation of projectiles, prompting a shift toward materials engineered specifically to disrupt high-speed rounds. The final armor in the chain responded to the relentless increase in projectile velocity by replacing metal and organic layers with engineered fibers and high-strength polymers, forming a ballistic shield that could arrest modern rifle rounds while remaining light enough for a soldier to carry. Early 20th century examples, such as the steel ceramic plates used by the British Army during the First World War, evolved quickly into all-ceramic and later aramid fiber vests, whose woven fabrics are tightly bonded to resin matrices that fracture upon impact, spreading the kinetic energy across a wide area. Field reports from the trenches of the Great War document soldiers whose bodies were saved by these plates when struck by shrapnel, while later laboratory tests on contemporary Kevlar and ultra-high molecular weight polyethylene panels demonstrate the ability to stop standard rifle ammunition at velocities exceeding 3,000 feet per second. The ballistic armor's power derives from its combination of tensile strength and controlled failure. The fibers stretch and delaminate, absorbing the projectile's energy without allowing it to pass through. Nevertheless, the material's limits become apparent when faced with armor-piercing rounds, high-explosive anti-tank munitions, or the kinetic energy of modern sniper cartridges, which can defeat even the most advanced composites. At this point, the armor reaches the apex of the historical progression. It offers the greatest protection ever achieved against the weapons of its predecessors, and no subsequent armor in the documented record surpasses its performance within the scope of human warfare. From hardened hide to the modern ballistic vest, each protective system rose precisely because the previous one could no longer meet the demands of an evolving battlefield. The chain of innovation illustrates a relentless dialogue between offense and defense, where every breakthrough in weaponry forced armorers to rethink material, structure, and design, culminating in a protective solution that, for now, stands as the most powerful armor ever fielded. The story ends here,